Okay, so in this short addendum to the lecture on Taylor and Maclaurin series, I want to show you with a little example how Taylor polynomials approximate the function near the center of that series, which is 1 in my example here. So I took the example done, one of the examples in the previous lecture, namely the Taylor series for the function ln of x, centered at 1. And you may recognize here in the summation that this is the summation term for the Taylor series for this function. And what I'm going to do is to define 3 functions which will be the Taylor polynomials of degree 1, 2, and 3. So the summation from 1 to 1 obviously is just the linear term. So notice it's x minus 1 already here. Then if I take the summation up to 2, that'll give me the quadratic Taylor polynomial. So these are the first 2 terms in the Taylor series. And then finally the third one, I mean the third degree polynomial, Taylor polynomial. With higher degree, you get a better approximation near 1. So let's start with the linear term, right? With the polynomial of degree 1. And we're going to show here the graph of the function itself, ln of x, and that of the first degree Taylor polynomial. So this is what we call actually in other applications the linear approximation. It's just a tangent line, in other words. So that's the linear approximation of that function near 1, which is the same as the first degree Taylor polynomial. Notice for this function, if you actually use values close to 1, like really close to 1, it's not that bad as an approximation. Basically, you can get a very small error if you get the closer you are to 1. On the other hand, if you expect, for example, to enter values, let's say more closer to 1.5, then you already have a substantial gap between the actual value of the function, which by the way is in blue, this is the natural log of x, and the approximated value. And the farther you are from 1, the bigger the gap is between the exact value and the approximated value. So let's sketch these now, the function with the second degree polynomial. And so notice already that the second degree polynomial, again in red, now follows the curve over a longer portion of the curve, or ln of x. So basically, if you are in this region around 1, you pretty much won't see with the naked eye the distinction between the exact value and the approximated value. So the error is very tiny. Once again, you move away from 1 too far, then already you have big gaps. And then finally, the third degree polynomial, again, you extend the area of coverage. So basically you can be even further away from 1 and you have a good approximation. And if you're curious, let's see what happens if I enter, for instance, a much bigger degree. Let's say the, let's make T10, which is the 10 degree polynomial. So that'll be, if you're curious how it looks like, this is it. And let's plot it together with the natural log of x. Normally I shouldn't see a difference between the 2 curves. Again, for a big portion around 1. Now, of course, you move away from 1 and already you see a huge difference, because here this polynomial, goes to, let's see, the degree is 10, but it has a negative coefficient. So it goes to minus infinity, right? If you look at the dominating term as x goes to infinity. But again, for a big portion of the domain, if I actually show you the graph between 0 and 2, it's a huge portion of the natural log of x where you don't see the difference between the Taylor polynomial and the function itself. And as I said in the lecture, typically you use lower degree polynomials because the idea is if you have a complicated function, you want to approximate it with an easier function. And obviously the linear approximation is the easiest one, but it's also the one that gives you potentially bigger errors if you move away from the center too much. All right, so I think that's all I have to say for this example. We'll see you next time.